Lamentablemente, por restricciones de viajes del NIH, nuestro primer ponente no puede estar hoy aquí con nosotros. Sin embargo, haremos una excepción y, aunque no es común en las conferencias inaugurales de GESIDA, posteriormente a sus charlas telemáticas, pues haremos un turno de preguntas de 5 a 10 minutos. Nuestro primer ponente es el doctor Richard Koup. El doctor Richard Koup obtuvo su grado en medicina en la Universidad Johns Hopkins y hizo su residencia en el hospital de Rhode Island. Además, el doctor Koup estuvo en el centro Aaron Diamond Ace Research Center, en New York University Medical Center y en la Rockefeller University. Ya desde los años 1997 a 2001, fue nombrado Stanford Professor y jefe de división de la Universidad de Texas, Southwestern Medical Center, y en el 2001 se mudó al NIH, al Vaccine Research Center, como investigador senior jefe del Laboratorio de Inmunología. Además, desde 2013 es también codirector del Vaccine Research Center. El doctor Koup pues, ha estudiado fundamentalmente el papel de la respuesta VIH específica y entre muchos de sus descubrimientos destacan la asociación entre la aparición de esta respuesta citotóxica y la bajada de la viremia durante la infección aguda. Además, analizó en detalle el papel del timo en la patogénesis del VIH y también demostró cómo las células VIH específicas eran las células que estaban preferencialmente infectadas y deplecionadas en la infección por VIH. También hizo hallazgos importantes acerca de la calidad de la respuesta VIH específica, más que la cantidad, y su papel crucial en el mantenimiento del control de la viremia. También ha hecho trabajos importantes analizando las células foliculares y en el tema que nos va a hablar hoy acerca de los anticuerpos neutralizantes de amplio espectro. Dr. Koup ha enseñado a más de 35 estudiantes pre y postdoctorales, ha sido autor de más de 300 artículos y participa en distintas editoriales de revistas muy importantes con alto impacto a nivel internacional. Es un honor tener aquí, que sea de vía telemática, al doctor Koup, y él nos va a hablar sobre anticuerpos neutralizantes de amplio espectro en prevención y tratamiento.
Hello. I want to thank the organizers for inviting me to present today. My name is Richard Koup, and I'll be talking about HIV antibodies for treatment and prevention. I do apologize for not being able to be there with you today, though that was my initial hope. I do have one disclosure to make, which is that I am listed as a co-inventor on a patent of the tri-specific antibody by Sanofi. I will cover three things in my talk today. First, the new generation of neutralizing HIV antibodies, then clinical trials for therapy and prevention, and what we've learned so far. And then, in order to attain clinical utility, how we're combining antibodies and engineering antibodies for improved potency, breadth, and half-life. So first, new generation of HIV neutralizing. Starting in 2009, numerous broadly neutralizing antibodies were isolated from selected HIV-infected donors. They tend to target 5 to 6 different sites on the HIV-1 envelope, and the best ones are both potent and broadly reactive against diverse HIV-1 strains. This shows a picture of the envelope trimer and the 5 different sites that are targeted by broadly neutralizing antibodies. The membrane proximal external region down near the viral membrane, the N332 glycan, or what we call the V3 site, the V1, V2 glycan site, or the V1, V2 cap, the CD4 binding site, and then the GP120, GP41 interface, which is actually a number of different epitopes. Listed beside each site are a number of different broadly neutralizing antibodies that have been isolated, but certainly not a complete list of the antibodies isolated to those individual epitopes. And the circled ones are the ones that are the furthest along in clinical development. How well do these different antibodies neutralize diverse strains of HIV? Well, that can be depicted in a graph like this, where I show 4 different epitope regions, the CD4 binding site in red, the glycan B3 in green, the B1, B2 in these blue colors, and the EMPER region in orange. 4 different CD4 binding site antibodies are listed down here, 2 against the B3, 2 against the B1, B2, and 1 against the EMPER. This is a panel of 208 multi-clade viruses, and for each antibody, each dot is how that antibody neutralized that individual virus in the 208 panel. What you can see is that for CD4 binding site antibodies, the further down on the y-axis, the more potent, you have reasonable potency, and you miss very few viruses that are shown as the percent resistance up at the top. For the glycan B3 and B1, B2 antibodies, they tend to be more potent, but less broad in that you're missing often up to about 50% of the viruses. The EMPER antibody, 10E8, is both potent and broad, but I need to bring up the point that the most potent version of this antibody, when tested clinically, gave this severe injection site reaction when given subcutaneously. So the Vaccine Research Center is certainly not developing this version of 10E8. We're going back and trying to re-engineer 10E8 to eliminate this reaction. But 10E8 is used in other combination therapies that I'll discuss and hasn't shown this problem when given intravenously. Let me talk now about clinical trials for therapy and prevention and what we've learned so far. So if we look at the clinical trials and what the indications are for the antibodies, I think for treatment of HIV infection, the main objective is to allow these antibodies to maintain viral suppression in individuals who have already been suppressed with antiretroviral therapy. So can these antibodies be used to maintain viral suppression? They've also been used to try and see if they can attack the latent viral reservoir as part of a cure treatment. For prevention of HIV infections in high-risk individuals, they're really being tested for immunoprophylaxis and long-acting PrEP indications. The first use of monoclonal antibodies in HIV therapy was from the Rockefeller group using the antibody 3BNC117, a CD4 binding site antibody. They gave this antibody to viremic individuals, and what you can see is that when given to viremic individuals, the antibody led to a decrease in plasma virus load that stayed down for about 2 weeks and then came back up. If the virus load in those individuals was low, it tended to drop the virus load even further and stayed down longer. This just shows normalized data of all those individuals. The VRC antibody, Brc01, was used in a similar trial, and once again you see the same thing. Viremic individuals, you give the antibody, virus goes down, comes back up after a couple of weeks. Those who had lower viral loads tended to go down lower and stay down longer. What you see here, however, is that there were a couple of individuals who did not respond very well, and when virus was isolated from all these individuals, those 2 individuals who did not respond well had much more resistant virus. The other way these antibodies have been used is to see if you can maintain viral suppression in individuals who are taken off of antiretroviral therapy. Two trials were published in 2016, one from the Rockefeller group using the monoclonal antibody 3BNC117, and a pair of trials from the NIH using Brc01. And the results were very similar. I just show you here the results from the Brc01 trial, where when people were given Brc01 taken off of antiretroviral therapy, the virus came back in all those individuals, and that return of viremia was delayed compared to historic controls. But importantly, when these viruses that came back were tested for sensitivity to Brc01, they were basically all resistant to Brc01. So the monoclonal antibody therapy had either induced or selected for resistant viruses. Now, from the use of antiretroviral therapy, we know that using this is what would happen if you use, let's say, AZT alone, which is why we use multiple different antiretrovirals for therapy. So we can do the same thing for monoclonal antibodies. And this was a very important study published by the Rockefeller group, where they used a combination now of two monoclonal antibodies, 3BNC117 and 101074, versus just 3BNC117 alone. And what you see is when people were taken off of antiretroviral therapy under coverage of these antibodies, the virus came back more quickly with 3BNC117 coverage than with dual coverage. And in fact, if they looked in the reservoir, and that reservoir was sensitive to both viruses, they tended to maintain viral suppression longer. And if the reservoir had resistant viruses, the suppression was not maintained. So combination therapy is going to be very important. And this just gives you an idea of the ongoing clinical trials. I show you here just the ongoing clinical trials about evaluating VRC monoclonal antibodies. I'm sure for the Rockefeller group, there's a similar list of multiple different clinical trials. And in addition to these, we have a number that are planned but have yet to be begun. So what you can see is that in the coming years, there will be a lot of clinical information coming out of individual and combinations of monoclonal antibodies for safety and PK, treatment and cure in infants, and treatment and cure in adults. So stay tuned, more data will be coming. What do we know about the use of antibodies for prevention? So we've known for many, many years that if you give monoclonal antibodies to non-human primates, you can protect them from infection. But we've really, until now, have not had any data on humans and whether passive protection by HIV-1 monoclonal antibodies is possible. But this year, that changed, and that's because of the AMP trial. So the AMP trial was a big collaborative effort between the HIV Vaccine Trials Network and the HIV Prevention Trials Network. It used VRC01 and gave VRC01 at either 30 milligrams or 10 milligrams per kilogram versus placebo to 4,600 individuals who were at high risk of acquiring HIV infection. This trial was initiated in 2016. The results came out in August of 2020 and were published in March of this year. It included men who have sex with men in America and Europe and women in sub-Saharan Africa. So what were the results from this trial? Well, when we looked at all of the data, what we saw is at the high dose, 30 milligrams per kilogram, there was a 29% decrease in risk of infection. But this was not statistically significant. So one could say that this trial was a failure, but remember, this was a trial to try and determine whether monoclonal antibodies could work, and if so, what dose was needed. And what you can see here is that with the pooled AMP results from these two trials, at 30 milligrams per kilogram, there is a signal, but it doesn't quite reach statistical significance. But let's look at the data a little more closely. If you look at all of the individuals who became infected, you isolate their viruses, and then look at the sensitivity of those viruses to VRC01, and then break it down by the placebo recipients, those who received the low dose and those who received the high dose of VRC01, it becomes very clear that the people who became infected who had received VRC01 only got infected with more resistant strains of VRC01. If people received no VRC01, they also got infected with viruses which were very sensitive to VRC01. So VRC01 actually protected individuals from these sensitive strains, but not the resistant strains. And you can now break the data down into sensitive strains, IC80 less than 1 microgram per ml, intermediate 1 to 3 micrograms per ml, or resistant greater than 3 micrograms per ml. And when you do acquisition analysis, what you see is that for sensitive viruses, there was 75% protection, which was maintained throughout the trial. For the intermediate or resistant viruses, there was no protection. And this just shows the forest plots of that, showing that for sensitive viruses, there was good protection, 75% prevention efficacy. Unfortunately, only 30% of viruses had that IC80 less than 1 microgram per ml, indicating that we need much more broad and potent monoclonal antibody combinations. And so this has allowed us to come up with a reasonable prevention target product profile. We feel we're going to need 2 or 3 antibodies or a tri-specific molecule. For practicality, we would like a dosage of 10 milligrams per kilogram IV or sub-Q every 3 to 6 months. The potency, IC80 less than 1 microgram per ml, covering 95% of strains, and probably as a frozen liquid. So let me talk now about how we can attain clinical utility by either combining antibodies and or engineering them for improved potency, breadth, and half-life. If you combine monoclonal antibodies, you can certainly get improved potency and breadth. This just shows potency and breadth against probably 200 different viruses using single monoclonal antibodies in these colors. So VRC07, PG9, PGT128, and 10E8 in these different colors. And what you see is that they're not all that potent. None of them come up to 100% coverage. But if you, in brown, combine any 2 of these, you get to greater than 98% coverage, and you shift to more potency. And if you go with 3 antibodies in gray or all 4 antibodies, you get full coverage and even more potency. So combining antibodies is one way of improving potency and breadth. Improved potency and breadth can also occur by taking 2 specificities and putting them on the same antibody, which is what was done by David Ho's group here several years ago, where they took one arm of the antibody and put an anti-envelope antibody, so 3BNC117, 10E8, some of the others I've told you about, and on the other arm, either an anti-CD4 or an anti-CCR5. When they looked in vitro at the coverage they got, what you can see is that for some of these combinations, they got incredibly good potency and breadth. And they decided to move forward with clinical development of this 10E8 IMAB combination that has been in clinical trials and has not shown the toxicity with the 10E8 component that I described earlier. Sanofi had a method to actually combine not 2 but 3 different specificities, the CODV format. And they developed a tri-specific immunoglobulin that included Brc01, 10E8 version 4, and PGDM 1400, showing over here those 3 different epitopes on the trimer. Now, one would think that maybe in this format that this specificity wouldn't be very well exposed, but if you look at the atomic structure, actually these 2 arms splay out and are both very accessible to the epitopes they're targeting. The type of breadth and potency that you get can be depicted in this sort of a chart. And here, once again, is the 208 strains of HIV-1. Here's the tri-specific molecule, and here are each individual specificity, looking at those 208 strains and whether they're sensitive, and if sensitive, what that's depicted by the shade from yellow to dark red, or resistance in blue. And what you can see is that with the combination, you really cover everything except just a couple of strains that are resistant. And this shows it in this other type of plot, where here I show the tri-specific over here on the right, showing the very good potency and breadth compared to any of these other antibodies that we have been talking about. What I should also tell you is that Sanofi has now out-licensed the technology for this program to a new startup company called Modex Therapeutics, and they're going to continue developing these multi-specific antibody products. In collaboration with Scripps Research and IAVI, the Vaccine Research Center has been trying to figure out which combination of antibodies they should be developing for full coverage. As I mentioned, we are not currently pursuing the MPER, so we really have decided to move forward with CD4 binding site, V1, V2 Apex, and V3 glycan combinations. And within that, as I have mentioned before, we really want to try and get to duplicative coverage of as many viruses as possible. So these groups are optimizing bNAbs in these different to these different epitopes for improved potency and breadth and use in combination. So this just shows antibodies to those 3 different locations, the V3, the V1, V2, and CD4 binding site. And once again, on this type of potency breadth determination, you can see that there are these areas of blue where all these viruses are resistant to any one of these different antibodies. Because we want to get at least dual coverage, when you look at this, you can see that these viruses are all covered by all 3 antibodies. These are only covered by 2 of the 3, and these down here are only covered by a single antibody. So really, when you think about it, we should be only looking, if we want at least dual coverage, at this part of the graph. In addition, remember, resistance we should define as an IC80 less than 1 microgram per ml. So anything in these lighter yellow colors should not be considered. So how does this look then if we take all of this into consideration? Well, if you look at an early acute clade C panel, looking at these 3 different antibodies, what you can see is that for 1 active, we're now at 93% coverage, so not yet at our 95%. And for 2 active, we're only at 63%. So we still need to improve potency and breadth of our antibodies. We've actually been trying to do that with the CD4 binding site antibodies by making mutations. We know that within the CD4 binding pocket, there is a hole into which can be inserted aromatic amino acids. So for the different CD4 binding site antibodies, we've tried different aromatic residues. We can eliminate a clash with the light chain of the antibody by truncating that. And we can add a framework mutation to the heavy chain to allow interaction with the adjoining protomer on the envelope trimer to help stabilize the interaction. In addition, we've been removing light chain glycans to try and improve the manufacturability of the antibodies. If you do that, what you can see is you can really improve potency and breadth. So if we look at Brc01 at this IC80 of less than 1 microgram per ml, we're only covering about 45% of our 208 virus panel. With Brc07523, it's 83%, and the improved version, we're up to about 95%. This just shows making those types of mutations in a number of different CD4 binding site antibodies, you can get certain lead candidates that are really much more potent and broad than the original ones shown here in red and blue. IAVI has also been making similar improvements in PGDM1400 and PGT121 so that we can now get much better combinations of antibodies, and this just shows 4 different combinations compared to the trispecific from Sanofi. And what you see now is at this IC80 less than 1 microgram per ml, we are now at over 98% coverage for all of these different combinations. And if we just take one of those as an example and ask about single versus dual coverage, what you can see is single coverage, we're at 98%. Dual coverage, we're at 85%. So we're getting there. Not quite there yet, but we're getting there. And finally, in order to have these antibodies given infrequently, we really need to increase the half-life. As you're probably aware, within the FC region of the antibodies, just a couple of amino acid changes will change the binding to the neonatal FC receptor, which leads to much longer half-life. So all of the antibodies currently in development really have either this or similar long half-life mutations. In conclusion, hopefully I've convinced you that improvements continue to be made in the potency, breadth, and PK of antibodies. How pre-existing and acquired viral resistance will affect the clinical utility of bNAbs is the focus of multiple ongoing clinical trials. Results from treatment and prevention trials have really helped define a realistic target product profile, and industry interest in bNAbs for treatment is helping to advance prevention programs. And the well-established relationships we have with prevention networks are key to clinical development of combination bNAbs. With that, I will just leave this up and thank all the individuals who were involved in putting this talk together, and thank you for your attention.
Well, we'll switch to English now. I hope Dr. Koup is ready for questions. So if anyone want to ask any question, this session is open for questions. So while anybody is going to the microphone, so Dr. Koup, so thank you very much for having this talk with us, and I will go on with one question. So let's be optimistic, and if we have the full potency and breadth and full coverage of these antibodies. So how will be the use in the real life for treatment, for instance, of these antibodies in relation? So what do we know about the effector functions of this antibody, for instance, ADCC response or effector functions of this antibody, and put this in context of the use or the future use of these antibodies in the real life? So how long will be given this antibody for treatment? How will be the dose or the use for treatment in relation to the effector functions of these antibodies?
Yes, thank you, Ezekiel. Thank you very much. Once again, I apologize for not being able to be there with you. But I think your question is very important and really covers a couple of things. I think that the real life use of these antibodies will probably start simply with, can we maintain suppression? And actually that question is in a lot of different clinical trials right now where people are suppressed. And then antibodies are being used alone or let's say in combination with other long-acting antiretrovirals like cabotegravir to see if we can maintain suppression. And I think if we can, it allows very infrequent dosing of your antiretrovirals, in this case being monoclonal antibodies. But you bring up a very important point about the effector functions. And clearly, antibodies don't just block virus replication through their effector functions. They may be able to fix complement. They may be able to kill virally infected cells. And through some of these activities, may be able to attack the viral reservoir. We don't know at this point whether they'll be effective in helping with a cure strategy, but it's certainly something that will be investigated in the future. And we're hoping that maybe through modifications of the antibody, something that Gilead has been doing to give them added effector functions, that they may actually, become part of the armamentarium for cure.
Thank you very much. Any other question? So, okay, so thank you again, Dr. Koup. It has been a pleasure to have you here with us for the questions, and thank you very much again. Thank you.
My pleasure. Thank you.